9.4 Models for Population Growth. In this section, we investigate different differential equations that are used to model population growth, the law of natural growth, the logistic equation, and several others. The law of natural growth. One of the models for population growth that we considered in section 9.1 was based on the assumption that the population grows at a rate proportional to the size of the population. The derivative of big P with respect to t equals kp. Is that a reasonable assumption? Suppose we have a population of bacteria, for instance, with size big P equals 1,000, and at a certain time it is growing at a rate big P prime equals 300 bacteria per hour. Now let's take another 1,000 bacteria of the same type and put them with the first population. Each half of the combined population was previously growing at a rate of 300 bacteria per hour. We would expect the total population of 2,000 to increase at a rate of 600 bacteria per hour initially, provided there's enough room and nutrition. So if we double the size, we double the growth rate. It seems reasonable that the growth rate should be proportional to the size. In general, if big P of t is the value of a quantity y at time t, and if the rate of change of big P with respect to t is proportional to its size big P of t at any time, then d big P over dt equals k big P. Equation 1, where k is a constant. Equation 1 is sometimes called the law of natural growth. If k is positive, then the population increases. If k is negative, it decreases. Because equation 1 is a separable differential equation, we can solve it by the methods of section 9.3. The integral of d big P over big P equals the integral of k dt. The natural log of the absolute value of big P is equal to kt plus big C. Absolute value of big P equals e to the power kt plus big C equals e equals big C times e to the power kt. Big P equals big A times e to the power kt, where big A open equals plus or minus e to the power c or 0. Close is an arbitrary constant. To see the significance of the constant big A, we observe that big P of 0 equals big A times e to the power k times 0 equals big A. Therefore, big A is the initial value of the function. Sidebar examples and exercises on the use of 2 are given in section 3.8. The solution of the initial value problem, d big P over dt, equals k big P. And big P of 0 equals P sub naught equals big P sub naught. And big P of t equals big P sub naught times e to the power kt. That's equation 2. Another way of writing equation 1 is 1 over big P times d big P over dt equals k, which says that the relative growth rate open, the growth rate divided by the population size close, is constant. Then 2 says that a population with constant relative growth rate must grow exponentially. We can account for immigration or harvesting from a population by modifying equation 1. If the rate of immigration is a constant m, then the rate of change of the population is modeled by the differential equation, equation 3, d big P over dt equals k times big P minus m. See exercise 17 for the solution and consequences of equation 3. The logistic model. As we discussed in section 9.1, a population often increases exponentially in its early stages, but levels off eventually as and approaches its carrying capacity because of limited resources. Big P of t is the size of the population at time t. We assume that d big P over dt approximately equals k big P if big P is small. This says that the growth rate is initially close to being proportional to size. In other words, the relative growth rate is almost constant when the population is small. But we also want to reflect the fact that the relative growth rate decreases as the population big P increases and becomes negative if big P ever exceeds its carrying capacity big M, the maximum population that the environment is capable of sustaining in the long run. The simplest expression for the relative growth rate that incorporates these assumptions is 1 over big P times d big P over dt equals k open 1 minus big P over big M close. Multiplying by big P, we obtain the model for population growth known as the logistic differential equation. Equation 4, d big P over dt equals k big P open 1 minus big P over big M close. Notice from equation 4 that if big P is small compared with big M, then big P over big M is close to 0. And so d big P over dt is approximately equal to k big P. However, if big P approaches big M, the population approaches its carrying capacity. Then big P over big M approaches 1. So d big P over dt approaches 0. We can deduce information about whether solutions increase or decrease directly from equation 4. If the population big P lies between 0 and big M, then the right side of the equation is positive, and so d big P over dt is greater than 0, and the population increases. But if the population exceeds the carrying capacity open, big P is greater than big M closed, then 1 minus big P over big M is negative. So d big P over dt is less than 0, and the population decreases. Let's start our more detailed analysis of the logistic differential equation by looking at a direction field.